So module 3 is regarding multicarrier modulation. Multicarrier. Multicarrier modulation. I'll simply call it MCM. Okay. Now you have learnt about single carrier modulation. All the modulations we have learnt so far is single carrier modulation. Now let us learn about multi-carrier modulation, where we are using more than one subcarriers. Subcarriers means they are frequency bands, and we are going to use more than one frequency band to carry information. Different information is being transmitted by different subcarrier bands, and we'll discuss the main idea behind it. The basic idea behind multicarrier modulation. The basic idea. The basic idea behind multicarrier modulation, it is to divide transmitted bit stream into substreams. It's to divide the transmitted bit stream into substreams. Divide transmitter bit stream into substreams and send this over different subchannels. Send this over different subchannels. And the subchannels, subchannels are orthogonal to each other. So we will encode in such a way that subchannels are orthogonal to each other. And we choose the subchannel bandwidth. We choose the number of subchannels. The number of subchannels is chosen in such a way that their bandwidth is less than the coherent bandwidth of the channel. The number of subchannels is chosen such that bandwidth of subchannel is less than the coherence bandwidth of the channel. So this is the basic idea behind it. It might feel a little abstract now. We'll get into details and we'll try to understand it further. Okay. So let us try to understand the concepts which we have told now in a little more detail. First of all, how is data transmission possible using multiple carriers? So data transmission using multiple carriers. How is this possible? So I told you there is an incoming stream, there is a data stream, and this data stream, it is getting divided into substreams. So divided into substreams, right? And how are these substreams chosen? It is chosen in such a way that the you can say it in terms of bandwidths. Substreams are chosen. You can say that the substreams are chosen in such a way that the bandwidth of each substream, it is less than the coherence bandwidth. You can, if I call the bandwidth of substream as Bn, this is bandwidth of substream. Bandwidth of substream is less than the this is the coherence bandwidth. Coherence bandwidth. Substreams are chosen such that the bandwidth of substream is less than the coherence bandwidth of the channel. Oh, this definition you said when you look at it from the frequency domain. From the frequency domain, you can say a definition like this. If you are seeing the time domain, then you can say the substreams must be chosen in such a way that the symbol time of each substream, the symbol time of each substream, okay, the symbol time of each substream is greater than the delay spread of channel, is greater than the delay spread of the channel. Okay, so if I write Tn is the symbol time of each substream. Tn is a symbol time of each substream, then Tn is greater than the delay spread. Suppose say the Tc. Tc is actually the coherence time, or you can roughly call it as the delay spread. Not exactly delay spread, coherence time is less than the delay spread, but for convenience, let me write just like this. Symbol time Tn should be greater than the coherence time or the delay spread of the channel, delay spread of the channel, right? Now let us see graphically how this happens. All this, you see the frequency domain, and this selection is done. Equivalently, you look at the time domain and you can see this this must get satisfied. Why is it like that, and how it is possible to think of it in this way in two domains? You can see a signal in time domain, or you can see it from the frequency domain. If you look a signal from the frequency domain, then you will see more of its bandwidth properties, frequency domain properties. If you see the signal from the time domain, you will see it in terms of impulse response and the delay spread, channel impulse response to the channel, and delay spread of the channel. Okay, so let us take a small example. We'll consider some examples, and we'll try to see how this selection of substream bandwidth and the selection of substream time duration, the symbol time on a substream, is taken. First of all, what do you mean by a substream? So if the incoming data is set for 6400 bits per second, so this is the data stream. So the data stream at 6400 bits per second. This I am dividing into various substreams, each of let's say 64 bits per second, 64 bits per second, 64 bits per second, and how many substreams are required. So I have 6400 bits per second. So I will be needing 100 number of substreams. There are 100 substreams, 100 substreams, each of 64 bits per second. So in total, the total data rate remains the same. It is 6400 bits per second. That remains the same. But the data stream is divided into a number of substreams, and the data rate on individual substreams, they are less than the data rate of the main data stream, right? So the data rate on each substream is less than the data rate of main data stream. Okay, or you can say more accurately, incoming data stream. Incoming data. So the incoming data stream is split into a number of different substreams. Each substream is having a data rate which is less than the main data stream data rate. And see how is this division done. So if you have n number of data streams, so if you have n number of substreams, then the data rate, suppose that this data rate of this mainstream, it is R, it is denoted by R. So the data rate of each substream, which is given by Rn, it is going to be R divided by n, right? Here Rn is equal to 64 bits per second. Rn is equal to 64 bits per second, and you can see this data rate has reduced. It was 6400 bits per second divided by the total number of substreams you are dividing into. That will give you the data rate on each individual substream, right? You can imagine this just like if there is a large pipe, okay, having a lot of water in it. Okay, yeah, there is water in this large pipe, and you are dividing this pipe into different small pipes. Yeah, so there is a connection going like this, there's a connection going like this, there's a connection going like this. Yeah, connection going like this. So I've divided this into 4 different streams of water, and the volume of water, the data rate is equivalent to the volume, or in information theoretic aspect you can call it as capacity, right? So the capacity of each of these small pipes, it is less than the mainstream, and this water which is incoming, okay, something coming at r bits per second, it is getting divided into r by n. Here n is equal to 4. And what about the volume at the other end? If I have a some collection mechanism where I am collecting all the water from all these pipes, it will be the same as R itself, because R was incoming, R got divided into a number of streams, and if you add the data rate on all these streams, I'll get back R itself. So that if you look this system from an input output perspective, then there is no change in data rate. But the incoming data stream, what I'm doing is I'm dividing that into a number of substreams, each stream having a lower data rate when compared to the incoming mainstream. So what is the advantage when you do like that? There comes the need of multi-carrier communication. We'll take an example, and yeah. Before saying the example, I'll just refresh your idea about coherence bandwidth. The coherence bandwidth is the range of frequencies for which channel remains a constant, okay, or approximately constant, right? So if I have the channel here, I'm only drawing single-sided for easiness of analysis. So if I have the channel like this, so this is the channel, and you can see there is a range of frequencies for which the channel remains almost a constant, right? And this range of frequencies, it is nothing but the coherence bandwidth, okay? Coherence bandwidth, BC. Coherence bandwidth, or it is a range of frequencies, the range of frequencies for which channel remains remains approximately constant. Approximately constant. For this range of frequencies, the channel, it is almost a constant, right? So this is the coherence bandwidth. So there is a concept of coherence bandwidth. Let me draw a channel. So this is a really I mean somewhat good channel, because for a considerable amount of bandwidth, considerable amount number of frequencies, the channel almost remains a constant. But in reality, you will not get a good channel like this. Let me draw another channel, a slightly problematic channel. Let's say the channel is uh, yeah, like this. So this is here. Now I'm seeing it from the frequency domain. I have the, so this is the frequency response of the channel, that is h of f. H of f is the frequency response It is a frequency response of the channel. It is a frequency response of the channel. H of f is a frequency response of the channel. You can see at some range of frequencies, at these frequencies, the channel is not so good. And here you can see there is some amount. Okay, let me draw it a little more flatter. Yeah, there is some amount of amount of frequencies for which the channel almost remains a constant. So here you can say the channel almost remains a constant. Yeah, let's say the response is like this. The channel is almost constant, and this is going to be your coherence bandwidth. Is going to be your coherence bandwidth, BC. So you have the coherence bandwidth of the channel here, and in the same figure, let me draw the signal also. Let's say that the signal is like this. Okay, let's say the signal is like this. Is your signal, that is x of f. X of f is the frequency domain of signal. X of f is the frequency domain of signal. So you have the channel, you have the frequency domain of the incoming signal to the channel. So you know that if you have a channel, and here in this case you have a wireless channel, x of f is the incoming signal. So this is a wireless channel. You have y of f at the other end. Frequency response is h of f, and this y of f is given by x of f into h of f. Right? In frequency domain, the incoming signal and the frequency response of the channel gets multiplied, and in the time domain, if you see the time domain, you have x of t and h of t. H of t is the channel impulse response, h of t is CIR, channel impulse response. You can see that the output y of t is going to be x of t convolution with h of t. It is x of t convolution h of t. So here we are viewing it from the frequency domain. So these h of f and x of f, they get multiplied just like this. They get multiplied, and when this multiplication happens, now we are talking about single carrier. Remember, we haven't got into multi-carrier. This is just single carrier. X of f is a single carrier. X of f is a single. We have a single carrier, and the bandwidth of single carrier is going to be, so this is going to be the, so the bandwidth is from here till here. This is the bandwidth of x of f of the single carrier. It is the bandwidth of single carrier. Let me denote it by b. Okay, b is the bandwidth of x of f, and you can see that bc, the coherence bandwidth, it is less than b. The coherence bandwidth is less than the bandwidth of the single carrier signal, right? So what happens when these two quantities get multiplied, h of f and x of f, when they get multiplied, you can see that there are some areas where the channel frequency response is very less. So in this area, the frequency response is very less. Similarly, in this area, the frequency response is very less. As a result, when these two signals get multiplied, here you will have signal degradation, signal degradation, or you can call it uh, loss of information. Because where is the information? The information is getting encoded in this bandwidth, right? So this bandwidth is having the information, and if these ends gets multiplied by a very low value, then their information gets tampered. Okay, their information is getting lost. So when you have and how can you regenerate this information? And at the receiver, let us think about that also. At the receiver, how can you get back this information which is having less value? The channel, the signal that is having a bandwidth of B. So these ends of the signal. So this much part, this much frequencies of the signal, and these frequencies of the signal, uh, they are getting multiplied with a low value of channel impulse response. So how will you get back the original signal from the receiver? So now at the receiver you have x of f into h of f, that is y of f. And how can you get back the original signal? That is equalization. So equalization is a method by which we are trying to get back the original signal. And here in a single carrier, for single carrier you have single tap equalization. So you have a single tap equalization. And how can you do the single tap equalization? Uh, so you multiply with, as you have only a single tap. So you multiply with a single value of h of f, right? That is y of f divided by h of f. So you do this process, the received signal divided by the frequency response of the channel, and you have a single tap equalization. But you can see a single tap equalization is not going to really work here, because here different values of signal frequencies, so different signal frequencies, they are getting multiplied with different values of channel impulse response. So you cannot divide y of f by a single value of h of f and get back the original signal. So single tap equalization is not so effective in this case, where you have the channel impulse response which is having a coherence bandwidth, and that coherence bandwidth is less than the signal bandwidth. And here you cannot equalize with a single value of frequency response here, because different frequencies of the signal are getting multiplied with different values of frequency response of the channel. So you cannot have a single tap equalization is not effective in this case, and you are going to lose some amount of information in this case, right? So another idea which came up is to divide this main signal, this x of f, into a number of substreams which are orthogonal to each other, which are having a bandwidth less than the bandwidth of the signal, which is having a lesser bandwidth than the coherence bandwidth of the channel, right? So a better idea is to use multiple subchannels, or in OFDM you call it as subcarriers. use multiple subcarriers or use multiple subchannels such that the bandwidth of the subchannel is less than the coherence bandwidth of the signal. So let me just show you how it works out. So again, I'm drawing the same figure, and you have the channel here. So channel is like this, and this is the channel frequency response h of f of the channel. And instead of a single carrier, I'm dividing it into multiple carriers. Okay, I'm drawing it in the same figure itself. This is one carrier, another carrier. Okay, in reality, the carriers will be very close to each other. I mean, there will be a number of carriers in this bandwidth area. This is your signal bandwidth B. I'm drawing a number of carriers. Okay, all these are carriers. My drawing is not so good. This is one carrier, another carrier, another carrier. Uh, these are substreams. These are substreams, and substreams are having a lesser data rate than the main stream, and also the bandwidth of the substream. The bandwidth of substreams is given by Bn, and this Bn is less than the coherence bandwidth of the channel. So you can very well see that. So if this is the coherence bandwidth of the channel, if that is the coherence bandwidth of the channel, then the bandwidth of these substreams. So these are the band. So this is the bandwidth of the substream. These substreams are having a bandwidth of Bn. Each of the substream is having a bandwidth of Bn, which is less than Bc. And what is Bn? Bn is equal to B divided by N. The bandwidth of the main signal. You are dividing it into a number of subcarriers with lesser bandwidth. Let us see how equalization can be done now. Now this let me denote it by x of 0. This is x of 1. This is x of 2, etc., etc. All these are subcarriers, and x of 0, x of 1, x of 2, they are the frequency points. They are the frequency points of the signal, right? They are the frequency points of the signal. You are seeing the signal from the frequency domain, and in the frequency domain you will be having a number of data points. So basically data points, yeah, not right if I say frequency points. They are basically data points itself. They are data points of the signal in frequency domain. In frequency domain. So x of 0, x of 1, x of 2, etc. up to it goes up to x of n minus 1. So you have in total n number of data points, and these data points, they are the different points in the frequency. If you have an n-point signal in time domain, you can convert it into frequency domain and again have n points in frequency domain. That will completely define the signal. Okay, it comes from the Nyquist sampling criteria. So you have n number of substreams here. Each substream is having a bandwidth which is less than the less than the coherence bandwidth of the channel. As a result, what happens is that here you have this point x of 0. In order to recover x of 0, you have the corresponding frequency response here, which is h of 0, and you can recover this value y of 0 as x of 0 divided by h of 0, right? And again, in a similar way, you can see here you have x of 1, and correspondingly at the same frequency you have h of 1, and you can recover x of 1 as uh, oh I'm sorry, this y of 0. So y of 0 is x of 0 into h of 0, and you can recover x of 0 as y of 0 divided by h of 0. Okay. It is not right for me to call it as 0 because 0 belongs to this point. This is 0 point. So let me call this as I'll say things in a little more in general sense. That is, let me call it as f1. This is f2. This is f3, and corresponding to x of f1, you have here uh, here you have h of f1. Corresponding to x of f2, I have here h of f2, and we know that y of f1 is equal to x of f1 into h of f1, and you can recover x of f1 as y of f1 divided by h of f1. And similarly here you can see y of f2 is equal to x of f2 into h of f2, and you can recover x of f2 as y of f2 divided by h of f2, right? So now there is no single tap equalization. So there are multiple taps in frequency, and for each of these substreams you have the equalization with the corresponding frequency response at that point, right? And the data rate of each of these stream is much lesser than the incoming data stream. So what really happens is basically what happens is the frequency selective channel the frequency selective channel, which means at different frequencies the channel is having different values of channel impulse response. The frequency selective channel, it is getting converted into a flat fading channel. It is getting converted into a flat fading channel, right? If the frequency response I can frequency response of the channel, if it is like this, it is a frequency response of the channel, that is h of f. So due to the number of substreams, it is getting divided into, so suppose say that this is one substream, this is another substream, this is another substream. Okay, so this is one substream having a bandwidth of Bn, and there are a number of substreams having a bandwidth of Bn, and you can see that for this substream, for this particular substream, for a particular substream, the channel almost remains a constant. So for this substream, the channel is flat fading. Flat fading means it is having a same value throughout the bandwidth of that substream. But if you look the channel as a whole, then the channel is a frequency selective channel. Okay, it is a frequency selective channel. It is having different values of frequency response at different points. But when you have divided into a number of segments like this, when you are dividing into a number of substreams, the channel almost remains a constant. The channel frequency response doesn't change much for that substream. So it is frequency selective channel, but flat fading for each substreams. When you consider each individual substream, you can see that the frequency response doesn't change much. So that is the idea of multi-carrier communication. So you are, when you're dividing it into a number of substreams, the frequency response of the frequency selective channel, it becomes like a flat fading channel for each substream. So in reality, you'll have a large number of substreams, and these gaps will be lesser. So for convenience to and convenience to see this, I've drawn it a little apart, but in reality you will have a large number of substreams, and you will see that these are really close to each other, such that these segments appear almost like a frequency flat fading channel. The streams might be like this. There might be a number, and you can see that for each segment of the stream, you will the channel appears to be flat fading for that substream, right? So that is the idea of multi-carrier modulation when you look it from a frequency point of view. You can also see this from a time domain point of view. That is, you can see it in terms of delay spread, uh, which is slightly more complex than this. Uh, we'll see that in the. I think the time is up. So we'll see multi-carrier modulation in terms of time domain in the next class.